for this presentation. Our next presenter is Omar Guzman, who also worked with Dr. Rebecca Thompson on a project on self-assembled monolayers. And this one is called, as you can see, Characterizing Surfactants and Adsorbed Asphaltene Mimics in Crude Oil Using Self-Assembled Monolayers, a Basic Science. Sounds anything but basic to me. I'm very excited. Omar, take it away.
Yeah, good afternoon, guys. My name is Omar Guzman, and I'm also excited to present how we can effectively characterize disorder and aggregation in heavy crude oil fractions using what are known as self-assembled monolayers. So just to kind of give some brief context into what we're discussing, talking about crude oil, as most of us know, crude oil has a very complicated matrix, right? From these simple 3 to 4 carbon chains, such as propane and butane, using refinery gases, all the way to these large aliphatic and aromatic complexes like asphaltenes and bitumen used in road construction. Now, because of these highly dense molecules present in crude oil, it tends to make oil very viscous. It tends to make oil very thick, thicker than blood actually. And this becomes an issue when retrieving it off the ground. So to the left image here, we just have an oversimplified image of a production well in which essentially oil workers inject water into a well. And that water should effectively push the oil, represented in orange, through another retrieval well. Now, because oil isn't as mobile compared to that of water, the water actually seeps through. So this is known as fingering phenomena. And this is an issue when retrieving it off the ground. We want to be as efficient as possible when retrieving oil. And if the oil isn't as mobile as water, that's just simply not going to happen. So the way that researchers have tried to eliminate this issue is with enhanced oil recovery techniques, EOR. I won't go into the specifics behind how all of these work, but there are 3 main ones: polymer flooding, alkali flooding, and surfactant flooding. And in essence, all of these simply decrease those interfacial tensions between the oil and the water interface, aka these adhesive forces. Or we can also increase the viscosity of water, thereby making it not as mobile compared to that of oil. So the reason I'm providing this context is because we're focusing on disorder of these crude oil structures. We want to focus on a very basic level as to what's going on between the packing, orientation, and all of these configurations of crude oil. And that might give a better approach or context to these more professional oil researchers as to what's actually going on whenever these processes are undergoing, right? Like whenever crude oil is going through this porous media, how is it aggregating? How are these things clumping together and whatnot? So that can ultimately bring more advantages to better EOR or just understanding these processes more efficiently, right? So the way that we're able to model these crude oil environments, as Ivan briefly already mentioned as well, is through SAMs, right? Self-assembled monolayers. The definition is pretty much in what the acronym stands for, but essentially we have a gold substrate. We dip it in a solution, specifically an alkane thiol solution, and this thing spontaneously chemiabsorbs onto our gold substrate, and it forms a monolayer. So the word thiol comes from sulfur, so we have a sulfur-gold covalent bond attached, and then that alkyl backbone just forms. And then we also have a terminal functional group, right? And it's really up to us to decide what we want that terminal group to be. If we wanted to make a polar functionalized surface, let's add a hydroxyl group there. If we want to make it a nonpolar surface, let's make it methyl terminated. If we want to dabble in pH, let's make a carboxylic acid, right? Put it in there. So it's really up to us. And as y'all see in a bit, I'm specifically going to do methyl terminated SAMs because we want to model crude oil's most basic nature, which are these paraffinic elements of crude oil, these alkanes. So we're making these monolayers, right? But how are we even looking at them? And that's where a specific FTIR technique comes into play. It's known as PEM-IRAS. I'm sure you guys forgot the acronym, right? But polarization modulator, infrared reflection, absorption spectroscopy. It's a handle, but in essence, we're shooting IR light at a specific grazing angle, and we can look at those vibrational modes in reflective surfaces. So that's kind of the apparatus in this left image here of what we're working with, our instrument. And this right spectra here is just an example of the data that we collect, right? It looks like there's a lot, but if we simply know what we can look at, we can truly digest a lot of information from here. So there's 2 types of peaks that we're mainly focusing on: methylene peaks and methyl peaks, symmetrical and asymmetrical modes correspondingly. And The key idea behind this is that literature has stated that methylene peak shifting to the right is indicative of disorder. So that's a way that we can assess disorder, that we can characterize disorder. And then we also look at intensity changes between these two peaks. We can have a better idea as to whether some species is outcompeting another one, or on whether we have orientational issues going on within the monolayer, as I'll explain later. But yeah, I mean, there's true beauty behind this if we simply know what we're looking at. So kind of further on, there were three main key experimental variables that I explored throughout my presentation. I first wanted to model the most basic structures of crude oil. Like I mentioned, those are the paraffinic elements, right? So we want to focus on methyl-terminated SAMs. I then switched to using deuterium alkane thiols. So deuterium is just an isotope of hydrogen with that extra neutron. And I'll explain a bit the reasoning behind that. And then finally, we also focused on incorporating oligoethylene glycol units. So these OEG units, this is actually the chemical structure that we were using. If you guys can tell, has a little bit of alkyl character, and then look at all these oxygens, right? This polar character. So this is amphipathic in nature. This is surfactant. Like I mentioned, there's surfactant flooding going on in these EOR techniques. So we can better understand those interfaces and what's going on to play here. We might have a better idea as to how to characterize all of this aggregation and packing, right? So we transition onto the first thing that I did in my research is we want to characterize these paraffinic elements, right? So there's three different alkane thiols that I used: dodecanthiol, octodecanthiol, and decanthiol. All of these are methyl terminated. They just have one methyl group at the top. The only difference behind these three is just the number of carbon chains, right? DDT is a 12 carbon, ODT is 18, and DT is 10 carbons. Now, panel A, we focus our attention to this right here, is simply telling us that we can actually characterize the differences between all of these three. Like I mentioned, all of these just have one methyl group at the top. And if we look at the methyl modes in panel A, which are these and these, there's not a lot difference between these two. So that's telling us that yes, we are only seeing one methyl vibrational mode in the symmetrical and asymmetrical, which corresponds to the chemical structures that are chemiabsorbing on our monolayer. So that's good news. This is working, right? So if we focus our attention now to these methylene modes, look at this blue is way higher in both of these. So what's the difference between this blue one and all of this red and yellow one? It's the backbone, right? This ODT is an 18 carbon chain, while alas, these two are just 12 and 10. So that's really distinguishable when we look at IR spectra, simply by looking at how higher these peaks are compared to this. So panel A is just showing us that yes, we can spot the differences between these. Now, if we focus our attention to panel B, this is where I want to start incorporating messier monolayers, create one-to-one dilutions of such. So panel B is showing us that we are actually showing methylene mode shifting in these, this and this peak right here. As I mentioned, methylene shifts to the right are indicative of disorder. And this horizontal line right here is, we're just quantifying those exact peak locations of the ODT here and here. And these peaks are a lot broader than this narrower peak, kind of shifting to the right as well as this. So at the end of the day, all this is saying, if you could sum this up in one sentence, is that we are seeing disorder when we are creating one-to-one mixtures of such ratios. So after dabbling on that, on those alkane thiols, I wanted to focus on the deuterated ODT. So like I mentioned, deuterium, it's a larger mass. So we wouldn't expect to see CH3 and CH2 peaks. We're going to start seeing CD2 peaks and CD3 peaks. And that's going to push that wave number region to the 2100. And the reasoning behind why I chose DODT is because I want to really focus on this 3000 region when looking at these one-to-one ratios. So I won't have to worry about having CH3 and CH2 characters in there because they're all going to be here, right? So this left spectra is just showing us that we can quantify the exact peak locations of that deuterated ODT, which is this dark blue here. And now if we focus on this right spectra here, look at the differences between these normal DDT and DT monolayers and in the ratios of such. Where did all of these methylene and methyl peaks go? They kind of almost disappeared, right? So what this is saying is that deuterated ODT is outcompeting this these shorter DDT and DT chains, which is actually something we already know. So larger alkyl backbones tend to outcompete shorter ones. So in a way, this almost served as like a proof of concept experiment, if you will. But it's a good way to start focusing on characterizing these specific regions, because we've never dabbled in this 2100 region before. And then onward from there, I started focusing on oligoethylene glycol. So as I had mentioned previously, OEG, this is acting as our surfactants, right? As our empathic molecules using surfactant flooding. And if we look at the structure of OEG, we have all these ether peaks. So you would think that this might be a way that we can assess whether this OEG unit is chemisorbing on our monolayer. And that's exactly the case. If we look at the 1000 wave number region, this peak right here is just the ether peak. And of course, this is just the OEG 100% by nothing. And then we slowly start adding more and more DODT. And we can see that intensity drop. So yes, that's indicative that this OEG is chemisorbing onto our monolayer. And if we focus on the 3000 region, this gives us similar data. It's the same results, right? In the 3000 region, this is just the CH2 character from the OEG. And now if we start adding DODT, look at the drop, right? We start getting more and more drops. So that's awesome. Pretty much, both of these graphs are simply saying that yes, OEG is chemisorbing, it's present, so now we can focus on what's going on in the mixtures in the 2100 region, which is what I'll actually explain in this next slide. So this is the 2100 region. If you guys remember, we had already characterized this deuterated ODT in the previous slide, in the deuterium ODT. And I'm focusing on what's going on with these two red spectra right here. So OEG 10 minutes plus DODT 10, and then the same one, but more time in DODT. And what we observe is actually something quite interesting. We should expect the CD2 backbone in the 30-minute DODT to be larger, which is like, it's a little bit hard to see, but these red lines right here. But that's actually not the case. It's actually way larger in the 10-minute DODT. So the reasoning behind this, or what we're actually hypothesizing, is that this might have to do with the orientation of our monolayer. So literature has once again stated that decreases in backbone are correlated with tilting angles in the orientation of our monolayers. So the PEM-IRAS is not only showing us disorder, it's also showing us the specific orientation of these monolayers, and that's awesome. We've effectively proved that we created a messier SAM, a messier monolayer, and a much more interesting one. So now I guess you could say that the next steps behind this is to actually maybe have some sort of actual quantification associated with this data, like what angles or what specific orientations. But this is an awesome starting point to moving forward. We also want to start introducing liquid phase experiments in which we are exploring liquid interfaces rather than just solid ones, because in crude extractions, everything's a liquid, right? We're pushing liquid through liquid oil. And then we also want to focus on aggregation. So Ivan had already previously mentioned he's working on coring physiosorption onto our SAMs. And we want to, little by little, get closer to these larger aliphatic and aromatic species. And at the end of the day, that's the beauty of it, right? We take something simple and expand it for other people to be able to have a better idea as to how these systems work. So all in all, I just want to say thank you for the American Chemical Society for the Research Petroleum Fund. Dr. Thompson, you're an awesome person. I really appreciate you these 4 years. Everyone in this room, these 4 years that I've met, I truly have gained something from all of y'all. So I greatly appreciate it, guys. Yeah, thank you. Yeah.
How does the disorder and aggregation shown in your IR data implicate for the future of petroleum refineries?
Yeah, so like this is a basic science. So if we can kind of understand why things are shifting or why things are aggregating where they are, researchers or higher level expertise researchers can maybe understand, oh yes, if adding two paraffinic elements in conjugation together is creating more disorder. What can we do to eliminate that disorder or separate this disorder? So that's why I actually titled this a basic science, because at the end of the day, we're focusing on a very specified section of this chemistry. If we were to actually grab crude oil and put it in a seham, then that's going to be very complicated to see. But it's a working stone. It's a working step to go up to a higher level. But yeah, no, for sure. Yeah.
How do the environmental conditions influence the absorption of asphaltene on surfaces?
On asphaltenes? So right now we haven't gotten to asphaltenes because there are these huge molecules, right? So Ivan is actually working on chlorine right now, and he's been able to kind of physiosorb that onto the SAM. But I mean, we can inference that environment plays a major role, right? That's why we're doing all of these studies, especially when we want to transition to liquid interfaces, because who knows if those asphaltene mimics are going to have some sort of interaction, van der Waals, with that solvent, right? So it's important to consider all of that, but I'm sure there are several implications within environment changes. Yeah, go for it.
I know you kind of touched upon it, but what are the next steps of using OEG, and can you explain how it behaves as a surfactant?
Yeah, so let me answer that second part of the question. So if we go to the structure of OEG, it's right here. This first part, it's all alkyl characters, so CH2, non-polar stuff, right? And then look at all these oxygens. This is all polar stuff. So a surfactant is simply an amphipathic molecule, right? So if we take a look at the soaps that we wash our hands with, all of these are amphipathic. That's how they emulsify the oils. And then whenever we draw a solvent, like water, through our hands, it pushes the oils out. It pushes all that non-polar stuff out. So that's essentially how surfactants, how soap work. So this is just a way we can mimic that, right? It's just a mimic of these surfactants. And then that first part of your question, can you repeat that first part of your question?
Yes, sorry. What are the next steps of using OEG?
The next steps of using OEG. Okay, so we were able to figure out the orientation. I think from here on, we want to start focusing on also using OEG with these asphaltene mimics. So maybe applying Ivan's project to this and maybe have a better idea as to how physiosorption is altered whenever we're focusing on these surfactant mimics as well. But yeah. Yeah.
Are you familiar with any environmental toxicities involved with this? I was like, this is like in our backyard. So like, whether it comes from human or the environment, or if it's a sustainable practice.
I do not know the answer to that question, I'm afraid. But by all means, I can look into it and I can let you know for sure.
With that, I'm going to invite Dr. Thompson up to present Omar with his cord and stole to celebrate everything he's accomplished in honors and at St. Edward's. He'll wear this with pride at graduation. And Dr. Thompson will, of course, have the chance to say a few things, and then we as an audience will get to congratulate Omar once again.
All right, well, the second half of a wonderful whole. Omar and Ivan have been wonderful to work with for all the reasons I said to Ivan, but I'm going to add, okay? When they started, they were in separate sections of Gen Chem. I had one in section 3, one in section 4. So I didn't realize they did everything together, but they do everything together. They joined my research group together and I said, you can do that, but you have to have separate projects. And they were game, okay? And they clearly what they've done is they've created kind of two halves of this very interesting exploration, helping me on progress with this, my very first independent grant. And I wouldn't have chosen other students to do it because I really felt that they could accomplish what we need to accomplish with this very important project. And Omar, as you could see from that data, right, those spectra data are tricky, right? That takes a heavy learning curve to figure out how to interpret those, how to present those, how to talk about them. And over the course of these years doing research, Omar has really figured out all of those pieces, and we've designed a lot of really cool experiments together as he talked about all these different explorations of messy surfaces. So once again, I'm really honored and excited to bestow this, and I am sure you're headed for an impactful career.
Oh, thank you.
Yeah.
I appreciate it. Thank you.
We'll do a hug.
Thank you.
And,
Thank you.
all right.
Appreciate it.